So let's continue with section 1.6. All right, from section 1.5, we had this theorem right here. If the limit as x approaches c of g of x is equal to L, and the function f is continuous at L, then the limit as x approaches c of f of g of x is equal to f of L. What does that mean? Okay, they better explain this, I think, in that is part. They're saying, what if we're taking a limit here, okay, of a composition of two functions? What it's saying we could do is we could pull this limit and put it to the inside here, like that's what that's showing there, and then evaluate f at that limit, as long as this limit exists and as long as my function f is continuous there, okay? So let's see how that's going to help us. That's going to help us with some examples we're going to do. Suppose we have an example and we want to calculate for part A the limit as x approaches infinity, of cosine of 1 over x. Let's try to use that theorem that we just looked at. We have an outside being the cosine, we have an inside of 1 over x. So to try to use that theorem, I'm going to bring the limit to the inside, limit as x approaches infinity of 1 over x. So I'm going to bring down the cosine. Now, what is the limit as x approaches infinity of 1 over x? That's one of the ones we memorized, right? It goes to 0. So that limit did exist. It is 0. Now, is the cosine continuous at that 0? Yeah, the cosine is continuous at all real numbers. So what is the cosine at 0 degrees or 0 radians? Let's look at radians, 0 radians. What is the cosine at 0 radians? Unit circle again. 0 radians, I'm right here. What is that cosine value? 1. Now in calculus, we're going to be using radians all the time unless it says otherwise, okay? We use radians in calculus just about all the time. Limit as x approaches infinity of natural log of x plus 1. Natural log of x plus 1 over x. Let me see, it's giving me a little gunshot to write things since the board moves. Natural log of x plus 1 over x. All right, outside function, natural log, inside function is this rational function. So let's try to pull that limit to the inside. So we're going to have the natural log of the limit as x approaches infinity of x plus 1 over x. Now, what happens if I try to evaluate this limit right here? I get like infinity over infinity, basically, right? That's indeterminate. Remember, we cannot determine what that is. So what do we do in this case? As we approach the infinity of a rational, didn't we divide the numerator and denominator by the highest power of x in my denominator? So let's do so. I'm going to have the limit as x approaches infinity, and we're going to divide x by x. We're going to divide 1 by x, and we're going to divide x by x. So I divided this term, and this term, all by x. So that gives me the natural log of the limit as x approaches infinity of 1 plus 1 over x all over 1, right? Now let's see, that'll be the natural log of, let's evaluate this limit. What does 1 go to as x goes to infinity? Stays at 1, right? How about 1 over x? What does this term go to as x goes to infinity? 0. And the bottom stays at 1, right? So what is that? That's a natural log of 1. Now remember, we could pull the limit inside. If the limit existed, which it did, it was 1, and this function is continuous there. Where's the natural log continuous? all positive numbers. That's a positive number. But what is the natural log at 1? Isn't that a value of 0? Now, what's really going to help you for natural logs is if you think about the graph of them, okay? Think about x-axis, y-axis, and this graph for your natural log function has a vertical asymptote at x is equal to 0. And the actual function itself looks like this. Goes through the point what? 1, 0. And it's a nice smooth curve that does like this. And it has an asymptote right here, so it never touches that y-axis, but it hovers along it. So you can see it's continuous what? For all this part right here, as long as what? I'm looking at x values that are all positive here. So think about that graph and that'll help you a bit. Just real quick, something extra. What does this look like? Does that look kind of like the coronavirus curve that you saw in the news over and over and over again? All right, part C. Part C, suppose we have the limit as x approaches infinity, the inverse sine of 3x over 6 minus 6x. All right, let's try to bring the limit to the inside here. So we're going to have the arc or the inverse sine of the limit as x approaches infinity of 3x over 6 minus 6x. If I try to evaluate this at infinity, I'll get some form of infinity over some form of infinity. So let's divide each one of these terms here, here, and here by x to the first. So we're going to have the inverse of the arc sine of the limit as x approaches infinity of 3x over x over 6 over x minus 6x over x. So that gives us the inverse sine of the limit as x approaches infinity of 3 over 6 over x minus 6. So that's the inverse sine of, what is this limit now? Top's going to stay 3. This part goes to 0 minus 6. So what does that give me? That gives me the inverse sine of 3 over negative 6. Or could I say that's the inverse sine of negative 1/2? But I can do better than that. Inverse sine of negative 1/2. Think about that for a second. How does this read right here? It reads, let me go ahead and write that down. That's very important. Helps us out quite a bit. This reads, the angle between, now I'll tell you what, let's put the angle theta. The angle theta, where theta is between and including negative pi over 2 and pi over 2, whose sine is negative 1/2. The angle theta, where theta falls between negative pi over 2 and pi over 2, sine is negative 1/2. That's from trig, right? Think about this for a second. the angle between negative pi over 2 and pi over 2. So on the unit circle, we're only looking between what? Between negative pi over 2 and pi over 2 for the angle whose sine is negative 1/2. How about a pi over 6? How about the point what? Square root of 3 over 2 comma 1/2? How about this reference angle of pi over 6 right here? Or actually, let's call that negative pi over 6. Where I'm at, square root of 3 over 2 comma negative 1/2, right? How do these run? These run cosine comma sine. Now, where do I have this? Where do I have the angle whose sine is negative 1/2? That's right here, right? Which angle is that? Negative pi over 6. So I'm going to call this negative pi over 6. Now, why is that not this angle of pi over 6 right here? Because my sine is not negative 1/2. I'm looking for an angle of sine is negative 1/2. Now, how come I can't think of it this time as, okay, well, right here, but what about this angle if I go all the way around like that? Because of this right here. This says what? The angle needs be between negative pi over 2 and pi over 2. In fact, whenever they start out with like an inverse sign like they did here, you need to make that restriction. Why? Well, you learned in trig that the sine function is only 1-to-1 from here to here, right? From negative pi over 2 to pi over 2. Because if we draw this portion right here, then what? It does not pass the horizontal line test, and it's not 1-to-1. So we got to take away that part and take away all this part. Next, we got some limits we need to memorize. Limit as x approaches 0 of sine of x over x is equal to 1. If you want to see how these two limits that I'm putting up right here are found, they're not found by the conventional techniques we used. Techniques we used up till now in this class won't work for these. So what do? We could prove these, and if you're interested in a proof, look in the book. But otherwise, we just memorize them so we can use them. So memorize those two. How are you going to use them? Well, for example, suppose you have the limit as x approaches 0 of 4 times the sine of x squared over 5x squared. Suppose we have the limit of that. Well, I could do a rewrite. I could say that's the limit as x approaches 0 of 4/5 times the sine of x squared over x squared, right? Remember what we could do with this constant is being multiplied? We could pull it to the front part of this limit. So I could say that's 4/5 times the limit as x approaches 0 of this stuff right here. And this stuff can be written as the sine of x over x times the sine of x over x, right? Because if I multiply these two, want to get x squared at the bottom. If I multiply these two, want to get sine of x squared at the top. Yeah. Now what's the limit as x approaches 0 sine of x over x? We said that was what? 1. So 4/5 times 1 times, what is this one? Limit as x approaches 0 sine of x over x. It's also 1. So what's 4/5 times 1 times 1? 4/5. I can't make that 5 for some reason right there. There we go.